Every winter, as temperatures drop and daylight fades, millions of animals across the globe prepare for one of nature's most remarkable survival strategies. They slow their hearts to barely a whisper, drop their body temperatures to near freezing levels, and enter a state so profound that they can survive months without eating, drinking, or even moving. This is hibernation, and it raises a fascinating question that has puzzled scientists and curious minds alike. If hibernation is such an effective survival mechanism, why don't humans do it? The answer to this question takes us on a journey through millions of years of evolution, revealing secrets about our past, present, and potentially our future. It's a story that begins in the warm forests of ancient Africa and might end among the stars, as scientists explore whether we could artificially recreate this natural phenomenon for space travel and medical breakthroughs. To understand why humans don't hibernate, we first need to appreciate just how extraordinary this biological process really is. When an Arctic ground squirrel prepares for winter, it doesn't simply take a long nap. Its body undergoes transformations that would seem impossible to anyone unfamiliar with nature's capabilities. The squirrel's body temperature drops to an astonishing 2.9 degrees Celsius, making it the mammal with the lowest recorded body temperature during hibernation. For 7 to 8 months, this tiny creature survives in what appears to be a state between life and death. Consider the little brown bat, another hibernation champion. During active periods, its heart pounds at an incredible 200 to 300 beats per minute, while it breathes 300 to 400 times per minute. But when winter arrives and hibernation begins, this frantic pace slows dramatically. The heart rate drops to just 10 beats per minute, and breathing slows to only 45 breaths per minute. This incredible metabolic slowdown allows the bat to preserve up to 90% of its autumn fat reserves throughout the winter months. Bears offer a slightly different hibernation story. Black bears don't experience the dramatic temperature drop seen in smaller mammals. Instead, their body temperature decreases by only 5 to 6 degrees Celsius, and their metabolism slows to about 75% of normal levels. This might seem less impressive, but consider this. Female bears give birth and nurse their cubs during this period, all while going 5 to 7 months without eating or drinking anything. Scientists actually classify this as winter dormancy rather than true hibernation, but it's no less remarkable. Alpine marmots demonstrate yet another hibernation strategy. These mountain dwellers wake up briefly every 2 to 3 weeks during their winter sleep to eat from their stored food supplies. These periodic awakenings are essential for regulating certain vital functions, showing that even in hibernation, life finds ways to maintain its delicate balance. The decision to hibernate isn't a conscious choice these animals make. It's an instinctual response to environmental pressures that have shaped their evolution over millions of years. When temperatures drop and food becomes scarce, hibernation becomes a matter of life and death. Insects die or become dormant, creating food shortages for insectivores. Plants wither or shed their leaves, affecting herbivores. Small mammals with rapid metabolisms face an impossible situation. They need constant food to fuel their high energy lifestyles, but winter makes such food nearly impossible to find. A shrew, for instance, must consume half its body weight in food every single day just to survive. During winter, finding this much food becomes impossible, making hibernation the only viable survival strategy. To prepare for this extended fast, animals like the alpine marmot spend summer months building up fat reserves that can account for nearly one-third of their total body weight. These fat stores become their sole energy source during the 7 month hibernation period. The physiological mechanisms behind hibernation are mind bogglingly complex. When hibernation begins, the hypothalamus region of the brain becomes highly active, acting like a master thermostat that controls body temperature and energy usage. Meanwhile, the brain's cortex regions, which handle energy intensive functions like thinking and movement, slow down dramatically. This allows the body to redirect energy solely to vital functions. Scientists have discovered that a naturally occurring substance called adenosine plays a crucial role in triggering hibernation. This molecule binds to special receptors, causing the heart to beat more slowly and with less force. Hormones from the thyroid gland also contribute by slowing metabolism, acting like the body's thermostat to minimize energy consumption. Perhaps most remarkably, hibernating animals' bodies can survive conditions that would be fatal under normal circumstances. They can function with extremely low oxygen levels without organ damage, thanks to special proteins that protect brain cells from dying. Some species produce high levels of vitamin C and special enzymes that neutralize harmful toxins that would otherwise accumulate during such prolonged inactivity. Even the immune system adapts to hibernation, rather than maintaining its usual vigilant state, which would consume precious energy. The immune system becomes suppressed during hibernation to prevent unnecessary energy expenditure and inflammation. All these changes combine to create what scientists call an energy-saving mode that allows animals to survive on a tiny fraction of their normal energy requirements. Given how effective hibernation is as a survival strategy, why didn't humans evolve this remarkable ability? The answer lies in our evolutionary history and the environments our ancestors inhabited. To understand this, we need to travel back approximately 7 million years to when human ancestors diverged from other primates in the warm, tropical forests of Africa. Our early ancestors lived in an environment that was warm year-round, with abundant food sources and minimal seasonal temperature variations. The tropical lifestyle profoundly influenced our evolutionary development. Since our ancestors rarely encountered the harsh winter conditions that drive hibernation in other species, their bodies never developed the complex mechanisms necessary for this survival strategy. Instead of evolving hibernation, human ancestors developed different adaptations that proved equally valuable. Bipedal locomotion, enhanced manual dexterity, and most importantly, larger brain capacity. When humans eventually migrated to colder regions around 100,000 years ago, they encountered true winter seasons for the first time. However, 100,000 years is far too short a time span for a species to evolve fundamental metabolic changes like hibernation, which typically requires millions of years to develop. Rather than waiting for evolution to provide a biological solution, humans use their intelligence to overcome winter challenges. They learned to control fire, create clothing, and build shelters. They remained active year-round, continuing to develop and advance their societies. This intellectual approach to survival made hibernation unnecessary. Interestingly, modern genetic research has revealed something surprising. Human genomes actually contain many genes associated with hibernation. At first glance, this seems contradictory since humans don't hibernate. However, these genes are evidence that all mammals share common ancestors and retain certain basic genetic mechanisms. This discovery has opened exciting possibilities for medical research. The presence of hibernation-related genes in humans offers hope for creating controlled, artificial hibernation states. Consider a severely injured patient whose metabolism could be temporarily slowed, giving doctors more time to perform life-saving interventions. When metabolism slows, tissues require less oxygen and are less likely to suffer damage. For example, a traffic accident victim with brain trauma normally faces the risk of brain damage within minutes of oxygen deprivation. However, hibernating animals' brains can survive with extremely low oxygen levels without harm. Scientists are working to activate hibernation genes in humans to create similar protective effects. This research could revolutionize emergency medicine, giving medical professionals precious extra time to save lives. Space exploration represents another exciting frontier for hibernation research. A journey to Mars would take approximately 7 months, and putting astronauts into a controlled hibernation-like state could reduce both the resources needed and the physical and psychological challenges of such a long voyage. NASA's space biology program is actively investigating this possibility, focusing particularly on molecules like hydrogen sulfide that might safely slow human metabolism. However, it's important to distinguish this research from cryogenic freezing, which belongs more to science fiction than current scientific reality. Unlike the controlled metabolic slowdown of hibernation, Cryogenic freezing involves extreme cold that can cause severe tissue damage. Current technology cannot safely freeze and revive human bodies, making this approach impractical for the foreseeable future. Hibernation research also holds promise for organ transplantation. Currently, organs for transplant have very limited preservation times, often resulting in the loss of viable organs. If scientists could induce hibernation like states in harvested organs, they could potentially preserve them for much longer periods, saving more lives and making organ matching more feasible. The implications extend beyond immediate medical applications. As we face climate change and resource scarcity, understanding hibernation might help us develop new approaches to human survival in extreme conditions. Some researchers speculate that controlled hibernation could even help humans survive long-term space colonization missions or extreme environmental disasters on Earth. Recent advances in hibernation research have revealed that the process isn't simply about slowing down biological functions. It involves complex cellular protection mechanisms, immune system adaptations, and metabolic reprogramming that we're only beginning to understand. Each new discovery brings us closer to potentially harnessing these mechanisms for human benefit. The story of why humans don't hibernate ultimately reveals something profound about our species. While other animals develop the ability to essentially pause their lives during difficult periods, humans chose a different path. We developed the intelligence and creativity to actively change our environment rather than simply enduring it. We built fires instead of lowering our body temperature, created tools instead of growing thicker fur, and built communities instead of sleeping alone through harsh winters. Yet the presence of hibernation genes in our DNA suggests that nature may have left us a treasure map of sorts. This genetic inheritance from our ancient past might hold keys to our future, potentially helping us travel to distant planets, survive medical emergencies, or adapt to changing environmental conditions on Earth. Hibernation research demonstrates that nature's library contains volumes we've barely begun to read. Every new discovery, every fresh understanding opens doors to possibilities we couldn't previously imagine. Perhaps someday we'll rediscover the hibernation ability our ancestors lost in Africa's warm forests, not through evolution, but through the power of scientific understanding. The question of why humans don't hibernate has led us to remarkable insights about our evolutionary past and exciting possibilities for our future. While we may never hibernate naturally like bears or bats, we might achieve something even more remarkable: the ability to consciously control and harness these ancient biological mechanisms when we need them most. In doing so, we would combine our species' greatest strength, our intelligence, with one of nature's most ingenious survival strategies.